Hello and welcome to our lesson on fundamental trig identities. Before we get to the work that we have to do with this lesson, I want to make sure we're clear on some vocabulary. For instance, I want you to understand what it means for something to be an identity. So technically, an identity is an equality. So when you hear that word, hopefully you're thinking like an equal sign, and things that have equal signs are equations. So an equation could be an identity, but by definition, an identity is an equality. It's an equation that holds true regardless of the value of the variable that's chosen. So for instance, if you had an equation like 2x plus 1 equal to 5, that's not an identity, okay? Because there's only one value I can plug in for x that's going to make that equation true. That's the one solution to that equation. However, if instead of 5 on this side of the equation I had the exact same thing, 2x plus 1, then now no matter what I plug in for x, I'm going to get the same thing on both sides of the equation. That equation is considered an identity. Or we have identity properties of addition. We have identity properties of multiplication. We have identity properties of distributive property. All these properties we've seen before in the form of identities. So, for example, the identity property of multiplication. We can multiply any number by 1 and not change its value. So as an identity for multiplication, we say any number, like a, multiplied by 1 would still be a. So that would be an equation that's true no matter what we plug in for a. Or for addition, if I add 0 to any number, I still get that same number back. So that would be the identity property. That would be an equation that's true no matter what value of a I plug in. And there are plenty of them, but hopefully you're seeing the idea, okay? So it's an equation, it's an equality, but no matter what the value of the variable, we get the same thing on both sides every time, which means that the two sides of that equality are interchangeable and we can replace one with the other at any time. And so, for instance, again, if we look at the distributive property, so when we are solving an equation like 2 times x plus 3 equal to 8 or something like this, we use our distributive property to create an identity here. When we distribute this, we know that 2x plus 6 is going to be exactly the same thing as 2 times the quantity x plus 3. So because this is the same, there's an identity there, we replace the undistributed form with the distributed form to help us solve. So it's sort of the idea with some of the work we're going to be doing, okay? So if we have an identity, the two sides of that equation in that identity, in that equality, they're interchangeable. And I don't know if I made this blank long enough, so I'm sorry. Interchangeable. I fit it there, but you're going to have to write tiny. All right, so we can replace one side with the other at any time. All right, so we're going to look today at some identities. In fact, they are the fundamental trig identities, meaning not that they're necessarily the most important, but they are the most commonly used. They are the ones that we are expected to memorize if we're going to go on to higher levels of math. So I would imagine that when you get to your calculus class, like the expectation is that you know the ones that we're going to talk about today. Now, over the next few topics, we're going to introduce more and more identities. I'll try to let you know which ones are important to store in the memory bank, but these are definitely on the list. So actually not all of them, but all the ones on the front of the notes that we're going to look at today, they should look familiar because we've sort of talked about them before. We just haven't called them identities, so we're going to do that today. So the first set we call the even or odd identities. And again, these should look very familiar. Think about what we were doing with graphs. So here, for instance, when it says the sine of negative x is equal to negative sine of x, what that's saying is that is an odd function. The same thing is said here, the same thing is said here, the same thing is said here. When you look at those four, what those are saying is if you put a negative input in, it's going to make the output negative. So if you change the sign of the input, it changes the sign of the output. That's what happens with an odd function or a function that has symmetry about the origin. If you have an even function like these two, then you can replace the input with a negative and it doesn't change the output. So the even or odd, sometimes I have trouble just remembering, now I made a big mess here, remembering some of these. What helps me to remember is the graphs, okay? So I'm going to take you to Desmos for a second, if I clean up my mess here, because if you see the graphs, you'll, again, if you can visualize what these graphs look like, or at least what sine, cosine, tangent look like, then their reciprocals just follow suit. So when we're looking at our sine curve, hopefully this picture was already popping into your head. Remember, for an odd function, every point and its opposite. So we see the symmetry about the origin happening with an odd function. So if I take the sine of pi over 2, I get 1. I see that happening here in quadrant 1. If I change that input from pi over 2 to negative pi over 2, it changes my output from positive 1 to negative 1. So changing the sign of my input changes the sign of my output. That's creating this symmetry about the origin. So sine of x is an odd function. It has that type of symmetry, and so does its reciprocal. Remember, its reciprocal, the cosine of x, or sorry, the cosecant of x does the same thing. Every point and its opposite. So those are both odd functions. They have the odd identity. Tangent does the exact same thing. Tangent has symmetry about, come on, there we go, symmetry about the origin. And I can see the same thing happening on the graph. Every point and its opposites. You've got this point here, you've got the same point over here, change the sign of the input, change the sign of the output. And its reciprocal, cotangent, has the same type of symmetry. So we have an input here with that output, a negative input, well, zero sign doesn't change, but again, you can see it graphically that it's going to be every point and its opposite. Almost all of our functions, well, 4 out of 6 of them, 2/3 of them, are going to be odd. The only ones that are even are going to be cosine and its reciprocal. So cosine is even. It doesn't have symmetry about the origin. It has y-axis symmetry. When it has y-axis symmetry, remember this is the one that's like x squared. That's if you change the sign of your input, it has no impact on the sign of the output. So for example, at pi, the cosine of pi is -1. Well, if you go and take the cosine of negative pi, you still get -1. So changing the sign of the input does not change the sign of the output. It's like x squared, right? 2 squared is 4, -2 squared is still 4, cosine behaves the same way. And its reciprocal, secant, does the same thing. Right? If I get rid of cosine, every point, not in its opposite like the origin symmetry, but if I change the sign of my input, it does not change the sign of my output. So that's the goal when we're looking at these even or odds, is to know that these two, pen back on, these two are the ones that are even. Alright, those are the only ones that are even, where I can change my input to a negative and it does not change my output. It's still the cosine of x. So obviously cosine of x is cosine of x, cosine of negative x is also cosine of x. So changing the sign of the input does not affect the output. The odds, like these two, are odd, and these two are odd. When you change the sign of the input, it does change the sign of the output. Okay, change the sign of the input, it does change the sign of the output. And that's going to happen every one of those odds. So, easy for me to remember graphically. Cosine and its reciprocal are even, the rest are going to be odd. Cosine and its reciprocal are the only ones that have the y-axis of symmetry. Okay? So knowing this, we can solve something like number 1. It says if the sine of theta is a -0.245, we should be able to find the sine of negative theta with no work, just using an identity. So knowing that this is an odd function, and when we have an odd function, that replacing our input with a negative makes the output negative. So instead of the sine of theta being equal to a -0.245, the sine of our negative theta, again, it's going to make our output negative. So the original output was a -0.245. We're going to make that negative. It's going to change the sign. So we're going to say the sine of negative theta is actually going to end up being a positive 0.245. Okay, so similar concept here. If the cosine of our angle is 0.7885, we should be able to find the cosine of the negative angle, knowing that this is an even function. And when I replace my input with a negative, it doesn't change my output. When I replace this with a negative, this is the same cosine that it was before. So if the cosine of theta is equal to 0.7885, then the cosine of negative theta is also equal to 0.7885. Okay? So those are the easy ones there. No work, just using the identity. And then let's look at the next example. So we have a new function that has a factor of sine, it has a factor of cosine, and it has a factor of x. And we are asked to determine if the function is even or odd. So we're going to use identities and this definition. How do we know if a function is even or odd? Oh, hang on 1 second, I gotta sneeze. Oh, man, I'm so sorry. Okay. How do I determine if this function is even or odd? So we said if we replace our input with a negative input and it makes the output negative, it's odd. If it doesn't change, then it's going to be even. And so that's what we're going to do. We're going to plug replace our input with a negative input and see what happens. So we want to replace x with, with a negative x, and then see what the result is. So here I have f of x, my function. I want to see what happens with f of negative x. So if I replace this x with a negative x, it's negative x. And then I'm going to multiply by the sine of not x, but negative x. And then I'm going to multiply by the cosine of not x, but negative x. And then see what happens. So let me do some simplifying using identities here. Negative x, I can't do anything with that. But I know that the sine of negative x is going to end up being negative because that function is odd. If I put a negative input into sine, it makes the output negative. So that part there, this part right here, I can replace with a negative sine of x. Negative input makes my output negative. Okay, and then here we have an even function. If I make my input on an even function negative, it doesn't change the output. So cosine of negative x is the same as the cosine of positive x. Okay, now I have two negatives. I have one here, I have one here, and a negative times a negative makes a positive. So if I rewrite my function, f of negative x, the two negatives cancel, so I'm looking at an x, a sine of x, and a cosine of x. And this function is exactly the same function that we started with. So f of x and f of negative x are the same. I replaced my input with a negative and it did not change the function. What does that mean? It means that this function is even. It also means if we were to put it on a graph that it would have symmetry with the y-axis. Okay, and actually we could confirm our work that way, but you're just going to trust me, right? And by all means verify that with your calculator, but that's exactly what you would see. Okay, those are our even and odds. They hopefully make sense based on the work we did with graphing, or even or odd identities. So now we're going to look at reciprocal identities. Again, these should look familiar. We talked about these with graphing. We talked about them when we worked on the unit circle. So we know that the cosecant is the reciprocal of sine. We know secant is the reciprocal of cosine. And we know cotangent is the reciprocal of tangent. So then we can answer a similar question to what we just did a few minutes ago. If I know that the sine of an angle is negative 0.245 again, I should be able to find its cosecant, because the cosecant of my angle is the reciprocal of sine. So in this case, I take the reciprocal of this number. So here we're going to say that the cosecant of our x is 1 over the negative 0.245. And that could be simplified, but I'm really not worried about that decimal approximation. It really isn't proper to leave a decimal in that fraction, but let's see. Can I get my calculator back in here? Mini version of my calculator. Delete all this, all my hard work. 1 divided by negative 0.245. Do I want a fraction? Oh yeah, the fraction is much nicer. So maybe I'm going to call this negative 200 over 49 to be more precise. But again, I would be okay with the other form of that, because the goal here is just to use the property, just knowing that sine is the reciprocal of cosecant, which, again, not new. Now, so we can use it to evaluate in situations like that. We can also use it to simplify a situation like this. So it says simplify sine of theta multiplied by cosecant of theta. So this is really sine of theta technically over 1, just like if I had x, it's x over 1. And we know that cosecant, again, is the reciprocal. Just saw that one a second ago, is the reciprocal of sine. So I'm going to replace that with 1 over the sine of theta. So what happens when I multiply here is that these common factors are reducible. And so we end up with just a value of 1. And this is actually one that we should know. If we multiply something by its reciprocal, that's going to happen every time we're going to end up with 1, like 2 times a half, or a third of 3, or a fourth of 4. Multiplying anything by its reciprocal is 1. That's an identity that hopefully we've seen before. A multiplied by 1 over A equals 1 every single time. So when I see sine multiplied by its reciprocal, or secant multiplied by its reciprocal, or cotangent multiplied by its reciprocal, those are always going to end up being products of 1. Okay? Nothing too earth-shattering there, I hope. Box that one in. Oops. Alright, so here we go. 2 more that should look familiar. The tangent. We talked about tangent on the unit circle being y over x, and then when we were graphing we said, well, the y value is just sine, and the x value is just cosine, so we can also call tangent sine over cosine. And then cotangent being its reciprocal could be called cosine over sine. So we got to be able to use these in similar fashions. We could use them to evaluate, or again, to simplify. So this one goes a little larger than I planned for in this space, so be careful spacing-wise. If you're copying this down on the note sheet, but we are going to try to simplify this mess by multiplying these 2 binomials. So let's start here. When I multiply sine of x times cosecant of x, I get exactly that. Sine of x, cosecant of x. And then I'm going to multiply here. That's going to be a positive sine x, secant of x. And then I'm going to multiply here. That's going to make a negative cosine x, cosecant x. And then finally, I will multiply here. That's going to make a negative cosine x and secant x. And then hopefully you're recognizing what we just talked about a second ago with some of these things, that this is the product of sine and its reciprocal. So this is technically sine of x, this is what we just saw, right? Multiplied by 1 over sine of x, so what's going to happen is that's going to become a 1. The same thing over here. Oh, I should have picked another color because I already used green. Let me do that again. Sorry, it's really going to bother me if I mess up all my colors. So let me do that again. Again, this we just saw. This is sine being multiplied by its reciprocal, which means we're going to end up with the product of 1. This, cosine and secant, those are reciprocals. So if I multiply cosine and 1 over cosine, again, I'm going to end up with 1, but this one's negative, so I get a negative 1 there. Here, what's happening? Do I have any other colors? Let me use, nope, black. Here, I'm multiplying sine and not its reciprocal, but I'm multiplying by the reciprocal of cosine. And so when I multiply again, this is over 1, I end up with, this was positive, the sine of x over the cosine of x. And then here, we have cosine, again, which is cosine over 1, multiplied by the reciprocal of sine. So nothing's going to cancel there. We're going to end up with this one's negative cosine x over sine x. Okay, so now a couple things. The positive 1 and the negative 1, those are going to cancel. And now we can use some of our quotient identities. The sine over cosine, that's right here. Sine over cosine we have to recognize as tangent, so we can just call this tangent of x. And then cosine over sine, that's right here, that's cotangent. So tangent of x minus cotangent of x is how that product simplifies. That's a much simpler version than what we started with. Okay, so using our reciprocal and quotient identities in that problem. And because I have this nice pen, I fit that in there really nicely, but hopefully you're able to do the same. Okay, so let's try another one. This one is a little bit easier. If I want to simplify this fraction, I want to rewrite these things. So I can use, again, there's reciprocal and quotient identities here. So cosecant, we know that one. Cosecant is the reciprocal of sine. So this is 1 over the sine of x. And then that's going to be over cotangent I can rewrite. Right? Cotangent is going to be cosine over sine. So cosine of x over sine of x, and now I have this complex fraction. Now I already know, because I've worked with complex fractions for years, that when the denominators in those two fractions within the complex fraction are the same, that they're going to end up canceling. But if you need to, you can rewrite this. This says 1 over sine of x from the top there is being multiplied by the reciprocal of the bottom. So we, in a division problem, instead of dividing the fractions, we multiply by the reciprocal. And what happens again, what I said was going to happen, is those denominators end up canceling. So what we end up with is 1 in the top of the fraction and cosine of x in the bottom. This is a better form of the answer, but not the best, because 1 over cosine, right, that's the reciprocal of cosine. Well, that has another name. The reciprocal of cosine is just secant. So the secant of x is going to be our final simplified form of this fraction. And then be really careful. I see often, and I am guilty of this mistake as well, sometimes I just say cosine, or I just say cotangent, or I just say sine, when really it should be cosine x, sine x, cotangent x. We want to make sure that we aren't losing our argument here. Like secant by itself means nothing. We're taking the secant of an angle. So there has to be an x or a theta or something in that spot. So we want to make sure that not to lose our variable when we're writing our trig functions. Okay? So far, nothing new. We've seen technically all of these identities before, just now we're classifying them as identities. On the back is where I want to show you a couple of new ones. And these are big ones. Again, these would be expected, you would be expected to know these. They're called the Pythagorean identities. And the first one should make total sense. Sine squared x plus cosine squared x equal to 1. And I say that and you're like, wait, why should that make total sense? So let's think back to our unit circle. Nope. Oh, I'm on my different app, sorry. My other app, I just hold it and it makes a perfect circle, sorry. I'm in a different one, this one. So in my unit circle, let me leave that on for a second. I'm going to try to make this picture kind of nice. Okay, that looks pretty good. So in my unit circle, when I have an angle in standard position, in the unit circle, I have this radius of 1. Right? And if I make a triangle out of that angle, then we said that this distance along the x-axis was going to represent our cosine of our angle, and that this distance along the y-axis was going to represent the sine of our angle, right? So y over x, sine over cosine, all the same thing. We can also see how we have a right triangle formed in here, that not only could we say that x squared plus y squared was equal to r squared, remember we said that before, but here we have, instead of x, we could say the cosine squared of x, or the angle, and then we can say, instead of y, the sine squared of our angle, or x equal to our radius in the unit circle is 1. So sine squared plus cosine squared, and really it gets confusing with x's and y's, which is, I shouldn't have done that. Let's say cosine squared, let's call it theta, and then sine squared of that angle theta is equal to our radius in general, r, but here 1. So the cosine squared theta plus sine squared theta equal to 1 comes directly from x squared plus y squared equals r squared. It's just the Pythagorean theorem, but it's applied directly to our unit circle. Okay, so this is again called a Pythagorean identity, and it should make sense based on what we've seen before with our right triangles. And this is a big one. Like, you are going to be expected to know sine squared plus cosine squared is equal to 1. It's a big one. Just in the same way you know a squared plus b squared equals c squared, this Pythagorean identity has got to get locked into the brain. Okay. Now the second Pythagorean identity, tangent squared x plus 1 equals secant squared, just comes from manipulating the first, and the third one comes from manipulating the first one as well. I don't want to get too much into that in the video here. I'm going to be happy to show you in class, but I want to not make this go an hour long, so just trust me, or you can look it up on YouTube and you can see some proofs for it, but they come directly from this first one. So if the first one makes sense, the other two come from this one. Now I want to point out also that there are alternative forms. So if sine squared x plus cosine squared x is equal to 1, like I could subtract the cosine x over and get an alternative form here and say, well, that means that the sine squared x has to be equal to 1 minus the cosine squared x. And also, so many things to say. When I say sine squared x, and I mentioned this one in class also, this is the quantity sine x being squared. Okay? This is not the same as the sine of x. Oh no, don't start, pen. Not the same as the sine of x squared in this way. So we don't want these two to be confused. If we lose the parentheses, then it's not equivalent. And so that we don't have to write the parentheses, we will put the square here to avoid having to write that. But sine squared x means the quantity of sine of x is being squared, not x being squared. Just for clarification. Okay, so back to this, Pythagorean identity. Again, I can rearrange these terms and get these alternative forms, so I could subtract the cosine over, or similarly I could subtract the sine over, so I could say cosine squared x is equal to 1 minus sine squared of x, or vice versa. Like, I could just move things around. Maybe I leave the sine squared where it is, and I subtract the 1 over. So if I subtract the 1 over, and then move the cosine over, right, this would be another form. Or maybe I leave the cosine squared where it is, and again subtract the 1 over and move the sine squared over, something like this. All four of these, they're all just manipulations of that first one. Alright, so then we have this one, tangent squared of x plus 1 is equal to secant squared of x. So again, some alternative forms. I could say tangent squared x is equal to secant squared x minus 1, or I could say tangent squared x minus secant squared x is equal to negative 1. Or I could say, what else? Maybe oh man, eraser. Maybe I can leave the 1 where it is and subtract over the tangent squared. I'm trying to think, how else can I manipulate this? There's like, I think 4 on all of these. What have I not done? Negative. Oh, this version. So I can leave 1 on this side and subtract the secant squared over and subtract the tangent squared over. And I think maybe I got them. Whatever. So you get the idea. I'm going to go one more round of manipulations here. So this is the third of our Pythagorean identities. So cotangent squared x plus 1 is equal to cosecant squared. Or cotangent squared is equal to cosecant squared minus 1. Or 1 is equal to cosecant squared minus cotangent squared. Or I could say cotangent squared minus cosecant squared is equal to negative 1. Or what else? 1 minus cosecant squared is equal to negative cotangent squared. So any kind of manipulation where you're just moving the sides by changing the signs, these are all valid and useful, but if you can at least remember the initial form, you're going to be good. And I would say this one in particular is very, very useful. Okay, it's like one of those things that's expected to be common knowledge. Okay, but we're going to use all of them here. So we can use them to do lots of things. One of them would be simplifying. So for example, here in number 8, if we're going to try to simplify, I would probably rearrange these. I have sine squared x plus I have a cosine squared x plus I have a tangent squared x. These two together, right, we see those right here. Sine squared x plus cosine squared x equal to 1 no matter what value of x I put in. So that's an identity, which means, again, those two sides are interchangeable. So I can swap out the sine squared x plus cosine squared x with 1. So now I have 1 plus tangent squared x instead. And again, that occurs over here. Okay, tangent squared x plus 1 is defined for us as secant squared x, no matter what the value of x. So now I can replace 1 plus tangent squared with secant squared. So this in the beginning simplifies down to just a secant squared x. Okay, nice and easy. Just using these things to replace other things. Okay. So looking at number 9, your instinct might be telling you to distribute, which is totally fine. That would be an acceptable way to approach this. But right out of the gate here, I see one of my identities, so I'm going to replace 1 plus tangent squared. So I have this cotangent squared x, or theta in this case, and then 1 plus tangent squared theta is going to get replaced with secant squared theta. So secant squared theta is going to go here. And then what? Well, both of these, one's a reciprocal and one's a quotient, so let's go ahead and rewrite those. Cotangent's cosine over sine, so I can replace cotangent squared with cosine squared over sine squared. And then secant is the reciprocal of our cosine, so I can call this 1 over cosine squared theta. And now I have these common factors in this product that can reduce. So then I would be looking at 1 over sine squared theta, which would be an okay place to stop, but that's the reciprocal of sine, and the reciprocal of sine we know is cosecant. And so we're going to end, and I really should have equal signs all the way through here, so sorry. This is going to be the cosecant squared theta. So a much simpler form than we started with, just using identities to swap things out. And I should put equal signs here too. Okay? So let's try another one. Unless you're feeling confident, you want to try this out. This would be a good place to pause the video, and try that. Alright, so 1 plus cotangent squared. 1 plus cotangent squared. Do I see that up here? Yeah, 1 plus cotangent squared right there. That's cosecant squared. So I'm going to go ahead and replace 1 plus cotangent squared with cosecant squared. So the top of this fraction becomes cosecant squared x. The bottom, 1 minus cosecant squared, I think I saw that in here too. 1 minus cosecant squared, yeah, right here, this is one of my alternative forms. It's equal to negative cotangent squared. So I'm going to replace 1 minus cosecant squared with a negative cotangent squared x. And now again I have one of my reciprocals in the numerator, and then I have one of my quotients in the denominator, so I'm going to rewrite that. Cosecant squared is the reciprocal of, or cosecant's the reciprocal of sine, so I'm going to make that 1 over sine squared of x. And then cotangent again is cosine over sine, so that's a negative cosine squared x over sine squared x. And we saw this happen just a little bit ago. I know I can rewrite this division as multiply. What's going to happen to those common denominators is they're going to cancel. So if I have 1 over sine squared x, and I multiply by the reciprocal of that denominator, which is a negative sine squared x over cosine squared x, again, those common factors, those common denominators which become common factors end up reducing out. And so then we have a negative, let's not lose that, 1 over the cosine squared x. And this again would be an okay answer, but we're trying not to leave fractions if we don't have to. And we don't have to here because 1 over cosine, that's a reciprocal of cosine, which we can also call secant. So this is going to be negative secant squared of x. Okay, again, in much prettier form than what we started with. Okay? So we can use a lot of these identities to simplify. Later we're going to use them for solving as well. We're going to use them to do some verifying of things. We can also use it in a case like number 11. It says to write cosine in terms of tangent. Write the cosine of x in terms of tangent of x. What that means is we want an equation that has cosine on one side and some form of tangent on the other side. Obviously those two things aren't equal, but this is what it means. In writing this in terms of tangent means we want it to be equal to something that has tangent in it over here and nothing else. So we don't want it to be equal to anything but something that has tangent in it. So we need to find an identity that's going to relate the two. Now I don't think there is a direct connect here. Like if I said write cosine in terms of sine, this would be the one I'm going to use because this one relates cosine and sine. Or if I said to write tangent in terms of secant, I'm going to use this because it connects those two. Now I'm going to use this one in the case we're looking at as well. This connects tangent and secant, but secant is directly related to cosine. So I'm going to use this identity, and you'll see how this flows in just a second. So I'm going to start with the tangent squared x plus 1 being equal to secant squared x. And then I'm going to take the reciprocal of both sides. Hopefully you're okay with that. If I have two numbers that are equal, like I know 2 is equal to 2, their reciprocals are going to have to be equal as well. And so I'm going to just take the reciprocal of both sides. Again, you're going to see why in just a second. So I'm going to make this 1 over the tangent squared x plus 1 and make this 1 over the secant squared x here, because now I have a place where I can introduce my cosine, right? 1 over, I just lost my train of thought. 1 over secant squared, sorry. The reciprocal of cosine is secant and vice versa. So if I rewrite that, 1 over... Why didn't I just... Hold on a second. I don't know why I just lost my train of thought. I take the reciprocal, 1 over secant. I feel like I'm going to have too many reciprocals here. I don't know. Maybe I don't need this step. Although I feel like I do. Okay, I'm just going to go with this. I'm sorry. I think it's the issue is, and you're going to run into this issue as well. So I guess it's good for you to be watching me or hearing me go run into this issue. Is sometimes there are multiple ways to do things. Okay, so let's go ahead and leave this tangent squared x plus 1 alone for a second. Secant, again, this is the reciprocal of cosine. So I can call... Oh, that's why I did this this way. So I can make secant squared 1 over cosine squared. Okay? Yeah, my brain was not working for a second. But here's the issue. Remember, what I'm trying to do is write my cosine in terms of tangent. So the reason I started with this identity is because I knew secant was going to be related to cosine. But what I'm going to try to do is solve this thing for cosine, because I want cosine on this side and I want tangent on this side. So I'm pretty close to that here, but I don't want to solve for cosine when it's in the bottom of the fraction. So what I did first, now I remember why I did this first, was I took the reciprocal of both sides. Okay, so I'm going to take the reciprocal of this side, tangent squared x plus 1, and 1 over secant squared. So now I can just replace the cosine squared on this side. Okay, so the cosine squared on this side, not doing anything here. Tangent squared x plus 1 on this side. Again, cosine and secants are reciprocals, so not only can we say that secant is the reciprocal of cosine, right, but we can say cosine is the reciprocal of secant. Okay, so they work both directions, and we've seen that. So now we're here, one step closer. Okay, I'm trying to solve this for cosine, because then on the other side of the equation I will have something that is in terms of tangent, which was the goal here. So all I have left to do to solve for cosine is get rid of the square, and we know how to get rid of a square. We're going to do that by taking the square root of both sides. So a little bit of algebra happens in here. So we're going to say this cosine of x all by itself is going to be equal to, remember when you take the square root, it's a positive and a negative, so it's plus or minus the square root of this expression that we are not going to try to simplify, because, like, I know tangent squared x plus 1 is secant squared, but I don't want this in terms of secant squared, I want this in terms of tangent. Okay, and we did it. So this is going to be exactly what we were asked to do. Write cosine in terms of tangent. So cosine is equal to, in terms of tangent, this is what it's equal to. Alright, so that's kind of a mess. You're going to see one of those in your homework assignment, but it's going to be an easier one. There's going to be a direct connection between the two that I'm asking you to write in terms of. So I think it's like write sine in terms of cosine. You're going to use the first Pythagorean identity and just solve it, and it won't be so bad. And hopefully you won't get stumped like I did. But if you do, don't feel bad, because this happens to everybody. Okay? So I got one left here, and this one left is an old problem, which I'm going to show you a new approach to. So we have done a problem like this before. If the tangent of an angle is negative 5/3 and the angle is in quadrant 2, remember the tangent of our angle tangent of our angle is equal to y over x. So we can look at it that way, which means, think about this in quadrant 2. Okay, here's our angle in quadrant 2. If we make a triangle out of that, our x value according to this is 3, and our y value according to this is 5. And the reason it's negative is because we're in quadrant 2, so that negative applies to that 3. But if we want to find the secant of an angle is the reciprocal of cosine, which again we were saying, but cosine, remember in terms of the ratios, cosine was x over r, so the reciprocal here would be r over x. Well, I know the x value is negative 3, but I don't have the r value. That's okay, I know how to find it. It's Pythagorean theorem. So remember we said r squared would equal x squared plus y squared, or r would be the square root of negative 3 squared and 5 squared. So that's 25 and 9, which is 34. So radical 34, which means the secant of our angle is radical 34 over x, which was negative 3. So that would be our solution. Okay, that's not new. We've done that before. But what I want to show you now is a new approach, a new way to do this problem. Not that we need another way, but I like for you to have the options and know how to use all the tools that are in your toolbox. So here is a new approach to this old problem. If I know the tangent and I want to find the secant, I can use the identity, again, that connects or relates the tangent and the secant. So we know from the second Pythagorean identity that the tangent squared plus the secant squared, not just kidding, tangent squared plus 1, what am I doing, is equal to secant squared. Okay, so tangent I know is negative 5/3. Well, what I need to do is plug that in, but square it here. So this tangent, negative 5/3 squared, I can just plug that value in, plus 1 has to equal the secant squared. Well, I can square this. Negative 5 over 3 times negative 5 over 3 becomes 25 over 9. And I'm going to try to add 1 to that, so I'm going to get a common denominator, which would be 9 over 9. And I end up with 34 over 9. So that should be looking familiar, but it's equal to secant squared. So if I want to solve for secant, which is what I'm asked to do, then I'm going to get rid of the square again by taking the square root. So I square root both sides, and so my secant is all solved for here. Secant of theta is equal to, technically should be a plus or minus. I can't take the square root of 34, so that's going to be stuck there, but I can take the square root of 9 and get 3. So now we're almost in the right, or the same place we were with our previous answer, but we just have to remember, so technically the solving introduces the positive or negative. We have to figure out which one of those we need, and it's based on the fact that we're in quadrant 2. So if we're in quadrant 2, remember what secant is. Secant is the reciprocal of cosine. In quadrant 2, cosines, x's, are negative. So the reciprocal should also be negative. So even though there's a plus or minus that's interjected when we solve, we have to remember that in quadrant 2, cosine and secant are negative. So we're going to say the secant of our angle is negative radical 34 over 3. Now some teachers only teach this in this section. I would never do that because I would never solve it this way. It's totally fine. Again, I want to show you the option. Maybe you like this as an option. To me, the picture and the angle and using the radius and Pythagorean theorem is a little easier. But these are directly connected, and you can see how the work kind of lines up and gets you to the same answer, obviously. So you have either approach. Again, there's going to be one of these in your homework. I don't care how you solve it as long as you get to the right answer. So you have the tools now. Got to use these identities to simplify, to maybe do some solving and maybe some evaluating. Hopefully you've got enough to go on here. It is challenging when you're first doing it, so don't beat yourself up. Mistakes are going to happen, okay? But just do your best to work on it, and as always, reach out if you have any questions. Until next time, take care.